In yesterday's class, we talked about um, uh, two different rules. One was the rule of consequence, the two different forms in that. One which said P, S, R, comma, R implies Q. Then we have P, S, Q. And we had another form. It said P implies R, R, S, Q, and we said this also, if you're able to prove the numerator, then P, S, Q. What this means is, if we know that in this particular case, P is a precondition for a program S, R, and R is an assertion that implies an assertion Q, then we can conclude that P is an assertion which, upon the execution of the statements S, can assert Q. This was the first one that we learned. And this was another assertion where we said if R is the precondition for a program S, which leads to the postcondition Q, then any other assertion that implies R can also be the precondition for program S. Then we looked at the null statement. Then we said, so the form precondition and postcondition are the same. This is equivalent to running a semicolon or a skip, whatever I'm talking about. Then we talked about the assignment statement, where we said P, E, X is the assertion which is true before the execution of the assignment, where E is an expression. Then we can conclude that assertion P is with respect to E is still true after the execution of the assignment. Then we learned about the rules of a composite statement, and which was essentially a sequence of assignment statements. Okay, this is what we saw. All right. So today what we're going to do is we're going to look at, so the assignment statement is completed. So we'll look at the alternative statement, and we all know that the alternative statement has two forms. If B, then S1, else S2. This is one form, and we have another form. If B, then S1. Okay. So let us look at these two forms of the alternative statement and see how we will work on it. So what we're talking about over here is the following. Basically, what we have, let us look at the first one. And here what we assume is that B is a Boolean expression S1 and S2 can be statements which may be composite. Okay, that's what we have. Now, uh, B is evaluated, right? If B is true, then the action is S1. If B is false, then the action is S2. Okay? So we draw it pictorially, for example. We write something like this. Here, if it evaluates to true, then we have S1, and if this evaluates to false, then we execute the statement S2. Okay, and both will lead to the same P. So what do we have here? There is a P here which is true before the alternative statement is started, and there is an assertion Q here which becomes true after the alternative statement has been executed. So let's look at the first part. B is true. Then S1 is executed, right? So that means what? This implies P and B is true before S1 is executed. Okay. So we have here P and B, S1, Q. The other situation is if B is false, or rather evaluates to false, then S2 is executed. This means what now? This suggests, implies that P and not B must be true before S2 is executed. Okay. If we can prove that both A and B are true, then the proof rule becomes P and B S1 Q, comma, P and not B S2 Q. Sorry. S2 Q, and what we can infer is that P, if B, then S1 else S2 Q is indeed true. Okay. This is the conditional or the alternative statement. Let us take an example. If A is greater than 0, then B is assigned the value of A else B is assigned the value of minus A. Let the initial assertion or the precondition be true. Okay. And let B be equal to A greater than 0. A greater than 0 and B is assigned the value of A, then we can conclude that B is greater than 0. Remember, this of the form PEX, right? What is the expression here? This assignment over here. So we have a variable name and an expression on the right hand side. Here X is B. We apply this rule, the rule of assignment. Now B is greater than 0. This implies B is greater than or equal to 0. Simple rules of arithmetic, right? And relational operators, right? Now, suppose B is not true. B is false. That means not of A greater than 0 is true, right? If not of if A greater than 0 is false, not of A greater than 0 is true, that means we execute the else part. B is assigned the value of minus A. And once again, we can conclude that B is greater than or equal to 0. Because now, if not of A greater than 0, then A is negative or 0. And again, applying the same rule of the expression, we can conclude that B is greater than 0. So A is negative or 0. If it's negative, then this makes B positive, and therefore we have greater than or equal to 0. We can therefore conclude, we therefore have the rule or conclude that true if A greater than 0, then B is assigned the value of A, else B is assigned the value of minus A, and we have B greater than or equal to 0 as the final assertion. So P, the assertion, the precondition is P here, which is true, and this is the post condition after the evaluation of the if statement. What this tells us is that this guarantees that no matter what the value of A is A we start with, B is always greater than or equal to 0. Let us look at the second variant of the if statement. If B, how does this rule look like? Is what we are interested in. Then S. So we have, again here, B is a Boolean expression, and if it is true, then the executor statement. S. If it is false, we do not execute, but it should lead us to the same Q. So we have start with P here, and it should lead us to the Q here, irrespective of what the statement is. So we're looking at P. We want to see how we can prove P if B, then S. Okay. So clearly there are two paths in this, and the two paths are case 1, S is executed. Case 2, S is not executed. So basically, for case 1, we must have P and B to be true. For S to be executed. That is, we need to prove that P and B, S leads to Q. This is case 1 for us. Case 2, on the other hand, let's say B is false. Then we have P and not B should imply Q. And we should prove this. So if these two are proved, then the proof rule becomes P and B, S, Q, comma, P and not B implies Q. Then we can state that P if B, then S, Q. Okay. Let's look at the final form of the alternative statement, which you have used in your CS2700 course. This is the case statement or the switch statement, as you might have called it. So what does it do? This is case expression of and L1 colon S1, L2 colon S2, Ln colon Sn is what it states. What is the meaning of it? Basically, if you look at it, E is this expression E is the selector for deciding which of S1, comma S2, comma Sn must be executed. And L1, L2, Ln are labels that correspond to the values that E can take. So if you want to draw it pictorially again, we have an expression which is getting evaluated. Some inputs are there to this particular expression. L1 equals E, L2 equals E, and so on. Have Ln equals E, and if it evaluates to L1, you execute S1, evaluates to L2, L2 are labels, Ln you evaluate, you execute Sn, and so on. And so now, so this is where what we need to show here is that P and X equals Li, Si, Q for I equal to, if you can prove this for each of the ln's, then we can conclude that P and X, let me write it a little differently. Okay. Let's say that let's say this xi are some, this li are some discrete values, then the proof rule becomes very similar to the long composition that we had. P and X equal to Ki, which is essentially Li. So this is the input assertion, and this is the evaluation of the expression to one of the values of Li. Si Q for I equals 1, 2, n, then we can say that P and X belonging to, notice this is a very interesting thing, K1, K2, any one of these values, it's actually one of K or one of N, then case X of K1, S1, K2, S2, and so on, will Kn, Sn will lead to Q. Okay, this is what the proof rule becomes. So let me stop here. So what we need to do is that we need to prove each one of these. The numerator needs to be proved, then we can conclude the denominator. So let me end this meeting over here.